Okay, so we're going to look at some force of gravity problems today. We're going to use what we learned in our last video to kind of help solve this first problem. So here's our universal gravitation equation right here. Force is equal to the universal gravitation constant, which is this, times the mass of object 1 times the mass of object 2 divided by the distance between their centers squared. So if we have the force of gravity between the Earth and the Sun, and we want to know what would the force be if we double each of their masses and the distance were tripled. So again, similar to last lesson where we have F nu equals gmm over d squared, and in this case I'm going to put mass of the Earth, mass of the Sun, and the distance squared, and then what we're going to do is we're going to see how that compares to the old force. So I'm going to double the masses and triple the distance. So in this space right here I'm going to put 2 mass of Earth and 2 mass of the Sun, and for the distance make sure that we get it squared. We have 3 times the distance squared. Again, what are we going to bring out front? So we've got a 2 times 2 in the numerator and a 3 squared in the denominator. This right here is equal to our old force, so our new force is 4/9 of our old force. What is the old force? Well, it's right there. So when I plug that into my calculator, I get 7.1 times 10 to the 22nd newtons as the new force. Okay, problem number 2. We've got Barbie with a mass of 50 kilograms and Ken has an unknown mass. We know the gravitational force of attraction between them, and we know the distance between their centers. So we're going to determine Ken's mass. So from our equation we have F equals G, mass of Barbie, mass of Ken, over the distance squared. And again, we're going to solve for mass of Ken. So the mass of Ken is equal to the force times d squared over G mass of Barbie. And now we can substitute and solve. So mass of Ken is equal to 4.53 times 10 to the negative 8 newtons times 2.50 meters squared divided by G, which is 6.67 times 10 to the negative 11th newton meters squared per kilogram squared, and the mass of Barbie, which is 50.0 kilograms. And again, we can do this all in our calculator. It's all multiplication and division, so we can just plug this all in. So I'm going to do that right now and show you kind of how that's done. The first thing I'm going to do is type in the 4.53 e negative 8 times 2.5 squared equals, so that's my numerator, and then I'm going to divide by these two quantities. So I'm going to divide by 6.67 e negative 11 and then divide by 50, and I get a value, and that is Ken's mass. And again, if I look at digits, I have 3 significant digits, 3 significant digits, 3 significant digits, and 3 significant digits. So my answer is good to 3 digits. So 84 point, and that becomes a 9. Units are kilograms. Again, if you're not sure about that, we can take a look here. Newtons and newtons cancel, meter squared cancels the meter squared there, and then we have a kilogram times a 1 over kilogram squared, so that reduces that out. So now I have a 1 divided by 1 over kilograms. And again, if you divide by a fraction, you can multiply by its reciprocal, so that comes out to be a kilogram for my unit. Number 3 is a little bit more challenging. Number 3, we're going to have to find forces that the sun is pulling on the Earth and that the moon is pulling on the Earth, or I guess it's a planet. And then we want to find the net force acting on the planet. So we're going to have a force this way and a force this way. So what is that going to look like? Good. I hope you're thinking about a resultant force where we're going to have to then do this and find the resultant of that. So we're going to find the x component and the y component. We'll find the resultant and the angle that's associated with that. So that's what we're going to do. I'm going to let you try to solve the forces here. There should be nothing new to solve for the two component forces, the one from the sun and the force from the moon. So do that, hit pause, and then check your work. Okay, here's the work that I showed to solve for this. Here's the force due to the sun. Again, it's g mass the planet, mass the sun, divided by the distance between them squared. Check this right here. Make sure that your distance unit is in meters. Again, right here we have Newton meters squared per kilogram squared. So our masses need to be in kilograms, and our distances need to be in meters. So that's important for you to make sure we do that conversion before we square it. This is what I got for the force from the sun. The force of the moon is very similar. The only difference is I have the mass of the moon. Kind of ran out of space on my paper, so I just continued it right off here to the side. And then the distance to the moon. So again, those were the numbers I got, and plugged those in. So the force between the moon and the planet is smaller than the force of the sun and the planet. So now I have two forces. I could put directions on these, which would be appropriate. Since the sun is pulling this direction on the planet, this would be a force that's north, and the moon is pulling this direction on the planet, so this direction would be east. So I have two forces now, and I want to find that resultant force. So I redrew the vectors and labeled them. So this is the force from the sun, this is the force from the planet, and I'm going to find this angle, and I need to find the resultant. So what trig function will I use to determine this angle here? Well, I know the opposite side and the adjacent, so I'm going to be using tangent. So pause the video and solve for theta using the inverse tangent. Here's the work. Again, theta is the inverse tangent of the opposite over adjacent. My opposite side is that value, my adjacent side is this value. I get 74.950 degrees, which then rounds to 3 digits to 75.0. And again, my direction is north of the east axis, so it's 75.0 degrees north of east. If I know the angle in either of the sides, you can then find the hypotenuse. So if I'm using this side, which trig function would I use? Good, this is the opposite side in hypotenuse, so I would use the sine. If I'm using this side and the angle, it would be cosine. So pick either of those. I'll let you decide, pause the video, and then see how to solve. I so happen to use the sine of that angle is equal to the opposite over hypotenuse. I'm solving for the hypotenuse, so it would be the opposite side divided by the sine of the angle. And again, go to 3 significant digits. I get that value. So this is the force, the resultant, and this is my angle that I get. So that is it for example 3. We'll move on to example 4 on the back. Again, here we're comparing two planets, their gravitational fields, and then also looking at their radii if we know how their masses compare. So it's going to be another one of the problems where we have F new and F old, and we're comparing those. So I'm going to let you try to solve this one on your own. Again, pause it, then you can see the answer, and then I'll talk you through it if you didn't get that answer correct. Okay, here's the work. I'm going to talk you through it. Here's the force on planet 1. It's g mass of whatever the object is times the mass of planet 1 over the radius of planet 1, because again the distance that we're discussing here is the distance from the center of that to an object that's on the surface, so that is a radius there. Same thing for planet 2, gm times the mass of planet 2 over the radius of planet 2 squared. And now we can start substituting. It tells us that planet 1 has a gravitational field 3.2 times that of planet 2. So for the force of 1, it's 3.2 times that of planet 2. We also know that planet 1's mass is 250 times the mass of planet 2. And we want to know, how does planet 1's radius compare to the radius of planet 2? So xr squared is going to be our denominator down here. I'm going to pull these values out in front, so I have a 250 in the numerator and an x squared in the denominator. And down here I have, if I pull this out, I have gm m2 over r2 squared, which if you notice right here is just f2. So that's a substitution there. f2's cancel and I'm left with 3.2 equals 250 over x squared. Solve for x squared and I get 8.8. And if I look back here, what did I say? I said the radius of planet 1 is equal to whatever x is times the radius of planet 2. So radius of planet 1 is 8.8 times the radius of planet 2. There's another way you could solve for this. What is a force on an object sitting on a planet? Well, that's just known as the weight. So the force on an object is the weight, or the mass, times little g. And that's also equal to big G times m, mass of the planet, over the radius of the planet squared. And if you cover this part up, what cancels? You should be able to see that the mass of the object cancels, and that's what we've said all along. Is little g dependent on the mass of the object? No. Objects accelerate at the same rate. It doesn't matter what their mass is, as long as we neglect air resistance. So that's what this is showing. So if you said the gravitational field is little g, you could do the same thing. So this would be gravitational field on planet 1 is big G, mass of planet 1 over radius of planet 1 squared, and G2 is big G, mass of planet 2 over radius 2 squared, and do the same thing. So G1 is 3.2 times G2. So I have G, and then it's 250 times as massive as planet 2. And we want to know, how does the radius of planet 1 compare to 2? So if we then bring this out front, 3.2 G2 equals 250 over x squared times gm2 over r2 squared. And what is this value right here? It is the same thing as G2. So this is 3.2 G2 is 250 over x squared times G2. So it works the same if you use forces, if you consider that a force, or if you want to do it as a little g as a gravitational field. Either way, you get the same answer. From here you move on to this step and get the same thing. So hopefully that helps you understand a little bit of what's going on with forces and gravitational fields.